All right, lesson 7.2 on sequences. We kind of did this when you were in compacted math or math 3, talking about sequences and series, a set of ordered numbers. Now we're going to have a calculus connection to this. I'm sporting my new Mathletics shirt, so I'm really proud of this shirt. All right, ready to go? So, the factorial definition of what does this mean mathematically. So this does not mean the number is excited. It might be excited, but this is what's called a factorial. And what that means is it creates a product. And the number you see, you start with, and then you count down integer-wise until you get to 1, and you multiply it together. So in other words, if it said 5 factorial, you go 5 times 4 times 3 times 2 times 1 and get your answer. If it said 3 factorial, you'd start at 3 and go 3 times 2 times 1, times, and so on. And then you stop at 1, obviously, because if you stopped at 0, that would be silly because the answer would always be 0. Okay. So if you simplify this in terms of what it means, this means n plus 2, and then if you subtract 1 to it, it would then be n plus 1, and then if you subtract it again, it would then be n, and then it would keep going. Now, if it goes n and then keeps going, at this point, it would actually be n factorial. The denominator is n factorial, so they would divide out, and that would be your answer. All right, turn the page. So we are going to deal with factorials in terms of sequences. Once we get there and practice it, I think you'll find it somewhat basic. Write out the first 5 terms of this sequence. So to write this out, you plug in 1, then 2, then 3, and so on. So if you plugged in 1, that's 1 over 1 plus 1. I got it. 2, that's 2 over 2 plus 1. Got it. 3 over 3 plus 1. This is simple, right? And then there's usually a pattern that then eventually you could see and then follow in terms of once you know the rule. So those are the first 5. I'll write out the first 5 terms of this recursively. So they give you the first one, and then they say to find the next term, follow this formula. 3 times whatever the term was before. So 3 times 5 plus 4. Got it. And then do it again, but this time you use 19. So 3 times 19 plus 4, that's 61. And then 3 times 61, that's 183, plus 4 is 187. And then again, 3 times 187 plus 4, I have the answer key, it's 565. But you get the idea. Number 4, write a recursive definition for this. So what's happening every time is you're multiplying by -3, right, to get the next one. So the formula then would be, all right, you're multiplying by, you're taking the term before, and you're multiplying by -3. We can also do it this way, that you could also write it with a plus 1. So the term ahead, you take the term before and multiply it by -3. They mean the same thing. Write an expression for the nth term of that sequence in terms of what you did. So this is what's called a geometric sequence. And a geometric sequence is exponential. It's in this form. So if you're multiplying times something, then this is the form, and I know it was a long time ago, for the geometric that goes with this. So the first term is 2. The base is the number that you keep multiplying by. That's -3. And then you have the exponent. And that's what's called a geometric model. So if you're multiplying by the same number every time, it's called a common ratio. And this is the general formula for that. All right, here it gets to more the calculus idea of what we're doing. Is that what happens when these things that are infinite series, do they converge to an answer or do they diverge and it doesn't exist? So if a sequence going to infinity actually converges to a number, that's what that L is. So does it actually converge to a number? If it's a geometric ratio, the ratio would be less than 1. It would converge to an answer. We'll see the ones that converge. If that limit exists, then we say it converges. If it doesn't exist, then the other word we use is diverges, that it doesn't converge to an answer. So if it says find the limit of this as it goes to infinity, what would the answer be to this question? We'll use n to infinity for n over 1 minus 2n. So the right n behavior means you go power term over power term. So if you go n divided by 2n, you get the answer 1 over -2, and that limit exists. So this is considered converges because it converges to an answer. Number 7. does this limit exist? So if I wrote it as a limit as n approaches infinity, does this converge to an answer? And the answer is no, because it's going to alternate. So when you put in an even exponent, it's going to be positive 1. And when you put in a negative exponent, it's going to be negative, or an odd exponent, it's going to be negative 1. So the two answers it could be, it's going to go back and forth between these two numbers as you put in even and odd exponents. So if I put in 0, it's 4. If I put in negative 1, it's 2. But it doesn't converge to an answer. It just oscillates back and forth. So we say this one diverges. In number 8, again, we don't have to write it as a limit notation, but if you wrote it as a limit notation as n approaches infinity, how would you approach this? Kind of like L'Hopital's rule, right? Like how would you approach understanding this, the right-hand behavior? And so first of all, I would use power property, where the exponent would go in front of the logarithm. And then if you have an understanding of this, n is more powerful than a logarithm, so the line increases faster than the logarithm. You could also take the derivative, but this is approaching 0 because the bottom is more powerful. If you decided to take the derivative with L'Hopital's rule, then it would be 2, and then ln n would be 1 over n, right? There's 1 over n, and then n would just be 1. And then you can really see that the bottom is increasing faster than the top. When you have a number over a variable going to infinity, any number over this, then you know the answer is 0. Number 9, determine whether these sequences are monotonic or bounded. Now, monotonic means it's only increasing or only decreasing, and bounded means that there's a lower number and a bigger number both, so that we have a number where every number in the sequence is bigger than a number and smaller. So like bounded means we have a low and a high, and all numbers are in between two numbers. If something's unbounded, we don't have these walls where we could say, oh, okay, all the numbers are bigger than 0 and all the numbers are smaller than 3. That's bounded. If it's unbounded, it just goes to infinity or to negative infinity, kind of what the work that we just did. So if I look at 9, remember it oscillates here. This is actually considered bounded because it's not going to infinity or negative infinity. So it's bounded between 2 and 4. It'll never be bigger than 4. It'll never be smaller than 2. It goes back and forth. But this is not monotonic because it doesn't only increase or only decrease, because it goes positive, negative, or it keeps going, it goes back and forth. It doesn't increase or decrease. It decreases, then increases, it decreases, then increases. That's the idea. If I look at number 10, if it's bounded, it converges to an answer. So if I say, what's the limit as n goes to infinity? If I look at power term over power term, you can see that it's bounded to 2. It converges to 2. So this is bounded. And as I put in numbers here, 1, 2, 3, 4, 5, 6, 7, 8, this strictly increases. It's not going to change direction at all. So if I look at the numbers, it only increases. And if we need to see it, so if I plug in 1, it's 2 over 3. Then if I plug in 2, it's 4 over 5. Sorry, if I plug in 1, it's 2 over 3. If I plug in 2, if I plug in, this is 3. And then it's 6 over 4, and then it's 8 over 5. So you can see this one's only increasing, and it's not going to turn. So because of that, it's bounded and monotonic. So eventually, it's going to get closer and closer to 2. And it's increasing as it goes there. Number 11. How about 1 over n? The limit as this goes to infinity, does it converge to an answer? And the answer is yes, it converges to 0. Because it converges, it's considered to be bounded because it converges. Next, as I plug in 1, 2, 3, 4, 5, you get 1, a half, a third, a quarter. This is decreasing, and it will continue to decrease as you put in numbers as it gets closer to 0. So this is considered not just bounded, it's also monotonic because it only decreases as it gets closer and closer to 0 for an answer. If I look at number 12, I want you to look at the power terms, n squared over n. When you divide, the top is more powerful. It's going to infinity. So this is unbounded because it doesn't converge to an answer because the top is more powerful. It goes to infinity. Is this strictly increasing or decreasing? So as you put in 1 and 2 and so on, so if you like start to look at 1/2, you put in 2, you put in 3, you put in all these numbers, these numbers keep going up, 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 and they'll keep going up, 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 all the way to infinity. So this is not monotonic. Sorry, this is monotonic because it's only increasing. Monotonic. But it's unbounded because it doesn't converge to an answer. All right, Mr. G Math, over and out. Till next time, we'll do the assignment together.